right, good morning. We'll make a start. Okay, so this is our second to last lesson on the motion topic. Last lesson we covered what is velocity and acceleration and calculating for acceleration using the idea of what velocity is, which remember is just speed in a particular direction. Now, the lesson previous to that, we covered distance time graphs, which is basically, how much distance was traveled over time. And we talked about what the different shapes mean in a distance time graph. Now we're going to move on to velocity time graphs, which is the next type of graph that you have to learn. And the trick is here, on a particular question, because obviously on an exam it's going to be a mix of distance time and velocity time. Because of that mix, you want to be careful and actually properly look at what is on the y-axis. Because some students, they see on the y-axis, some students see a motion graph and then analyze it like it's a distance time when it's actually a velocity time graph, or analyze it like it's a velocity time graph when it's actually a distance time graph. So you really have to look at what is on the y-axis, whether it's velocity or whether it's distance, and then from there do your analysis. So let's start off first by having a look at the different shapes a velocity time graph can make. And if you were here for the distance time graph session, you would remember that we did the exact same thing with a distance time graph, but even though the shapes are similar, it's going to mean different things. So let's start from the left-hand side here. Velocity and time, we have a straight horizontal line that's at 0. So if as time is increasing, going from left to right, velocity is staying at 0, well, how would you describe this motion? Velocity staying at 0 over time. Well, the object would be stationary. Because it's at 0 velocity over time, meaning it's not going anywhere, meaning it has no speed / velocity, so it's going to be stationary. Next, let's say that there was, we still have a flat horizontal line, but it's at a particular number. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8. So this is at 8. And as time increases from left to right, the velocity is not changing, it's still at 8. Remember, velocity is measured in meters per second, and it's just the speed of direction. So it's moving at a constant 8 meters per second. So we say this is constant velocity, or you could also say constant speed. It'll be the same thing. Remember, velocity is exact same thing as speed, just in a particular direction. Now, let's look at the next set though. As time increases, velocity went from 0 and is going up. And because it's a straight line, it's going up by a steady amount each time. So like at, for example, 1, 2 seconds there, the velocity was 2. At 4 seconds, the velocity was 4, etc., etc. So, how would I describe this then? Velocity is going up over time. Velocity is increasing over time. Remember last lesson we talked about this key word known as acceleration. Acceleration means you're just changing your velocity over time, right? So because the velocity is increasing as time is increasing, this object is accelerating, and it's a constant acceleration, meaning it the the acceleration value is not changing. If this graph was curved, that means the acceleration was changing, but it has a constant acceleration. Now, you can probably already guess the next shape and what it means. Time is increasing, and velocity, you'll notice, is dropping. It's going downwards. So it's going from up here, down, slowly down as time increases. It is increasing. Another keyword we learned last lesson. The object is decelerating, meaning it is slowing down. So I'll say speeding up over by here because velocity is increasing over time, and decelerating, slowing down because velocity is decreasing over time. Just as a quick recap of distance time graphs. I'll put dt as distance time. If our distance time graph had this shape, it would also be stationary because it would be at 0 as time increases. If it had this shape, it'd also be stationary because the distance is not moving as time increases. But if it has a straight diagonal line like this, if it had the exact same shape as this, distance is increasing as time is increasing. So it's moving at a constant speed. And if it had a shape like this, it'd also be a constant speed, just returning to the start. That's why I said at the very start, you have to look at what is written on the y-axis. Because you'll notice, aside from the very first one, each shape is going to mean something different whether you're looking at a distance time graph versus a velocity time graph. So you have to be aware of what is written on the y-axis to be able to analyze properly. Now let's have a look at seeing if we would be able to extract information from a velocity time graph. Okay, so 2 lessons ago we talked about something called the gradient, which is something you learned in math. And remember, the gradient is basically like the slope of the graph, also calculated via rise over run. So the gradient is just the slope of the graph. How much is it going up by? And based off of the x-axis, how fast is it going up? So the gradient is this slope here. So like, for example, let's say we had 2 graphs and we had a graph like that versus something like that. This is a higher gradient and this is a lower gradient. Okay, so what does the gradient mean then? One thing I want you to notice is that, remember, the gradient is calculated by rise divided by run. Rise is the change in the y-axis and run is the change in time. Change in the x-axis. Well, in this case, the velocity time graphs, the change in the y-axis represents velocity. So the rise represents the change in velocity. I'm going to write change in v. And the run is the change in the x-axis. And so in this case, it's the change in time. Think back to last lesson now. What is another name, well, what is the value that you can calculate through change in velocity over time? Remember, last lesson we calculated a bunch of acceleration questions, and the acceleration formula, remember, is a equals v minus u over t, which is basically just the change in velocity over time. So gradient is rise over run. In this case, rise is change in velocity, run is change in time. So you can guess, you can already predict that the gradient, if we calculated the gradient of these graphs here, the gradient of a velocity time graph, I'm going to write of a VT graph, is equal to the acceleration. So if I were to calculate the slope of this graph, I would be calculating the acceleration of this object. Now, just as an example, if you look at this, right, over by here, change in velocity, the rise. Well, velocity is not changing, it's staying at this 8 point over time. So the acceleration in this case is 0. Over by here, change in velocity over time. Well, I'm going to say that it started at 0, 0. So the change in velocity is rise was 4, run was 4. So the acceleration is 1 meters per second squared. And this object here is slowing down, so it's decelerating as well. So you're going to get a negative value from a negative slope. The reason why I went through all of that, instead of just telling you that acceleration is the gradient of a velocity time graph, is to help you understand why the acceleration is the gradient of a velocity time graph, because it is all connected. The formulas that we did, the formula calculations that we did yesterday of acceleration equals v minus u over t, that also applies to these graphs. They're not separate things, they're the same thing, we're just graphically representing them. And everything that you learn in maths, the gradient, rise over run, all of that applies as well. They're all connected things. Now, for higher tier, so if you're taking foundation, you don't have to worry about this section, but in higher tier, you may be asked to calculate for the distance traveled by looking at a velocity time graph. And I notice that I said by looking at a velocity time graph, not a distance time graph. Because obviously it's easy to find distance traveled through a distance time graph. You just look at the distance on the y-axis. But with these graphs, velocity time, it's not straight off the bat obvious how you find the distance traveled. So like, you're given this object, it's traveling at this speed / velocity over time, it's changing its speed. Now you're being asked how much ground it covered. Well, that seems a bit difficult, but there is an easy way to do it. And the easy way is all you have to do is calculate the area under the graph. And the area under the graph gives you the distance traveled. And the reason why that is, and I'm just gonna say this, you don't have to remember why. That's not going to come up as a question. You could just memorize this. Area under graph is distance traveled. But for those of you who are a bit nerdy like me and like to see the connections, let me tell you this connection. Your minds are going to be blown. Okay. So, hang on. Where's my thing? Right. You guys are already familiar with the formula speed equals distance over time? Yeah? Well, the formula is pretty much the same for velocity, it's just distance over time. Sorry, my mic cut off. The formula is just the same for velocity, it's just distance over time as well. And to calculate distance then, you just have speed times time. Just from rearranging, because you move time to the other side by timesing both sides by time. So distance is speed times time. Speed can also be known as a velocity, because velocity is just speed with a direction. So distance can be calculated with velocity times time. Now, let's have a look at this. On the right hand side, we have a triangle here. To calculate the area under a graph, remember how it's base times height? Well, divided by 2. Base times height, but it's pretty much base times height. Base times height happens to be times time times velocity, which is equal to the distance. I mean, come on, that connection right there. So this formula that you've been learning, speed equals distance over time, it relates to this graph. It maps onto this graph perfectly. We can calculate the distance traveled by the area under the graph, because to find areas of a general shape, it's base times height, and base times height happens to be the formula for calculating distance traveled. That was my rant done for the day. But the key thing you need to know is area under the graph is distance traveled. Now let's do an example. Okay. So my example here is calculate the displacement. So basically calculate, oops, this should say, I want this to say velocity. That was my bad. I want this to say velocity in meters per second. Okay, calculate the displacement. So, as this is a velocity time graph, the displacement is the distance traveled. So I need to find the area under the graph. Well, by that I mean the under the graph line. So I'm going to shade it in. Well, actually I'm going to highlight it. Let's get a highlighter. There we go. This will work. So this whole area by here is what I'm calculating for, because it is the area under the graph to the to the x-axis line, basically. So this is the area under the graph. So I'm calculating for all of that. Now, there's there's two main formulas you need to remember. For those of you who are more comfortable with using the formula for area of a trapezium, feel free. I personally prefer to just memorize the area of a triangle and area of a rectangle. So I'm going to do it that way. It's a bit longer than if you calculated using the area of a trapezium formula, but the reason why I'm avoiding the trapezium formula is just because I know that when you guys did it in maths, it was very short. So you might not have it at as well memorized. But area of a triangle is base times height divided by 2. and area of a rectangle is just base times height. So notice that the shape I have here that's highlighted in blue, notice that unfortunately it's neither a rectangle or a triangle. It's this oblong shape. But I can split this apart into a series of rectangles and triangles, can't I? And if I calculated the area of each separate piece and added them up together, I can find the total area. So I'm looking at this shape and I notice I can split a triangle off, a perfect triangle off here. Look at that. And if I calculate the area of this triangle, I can then add it on to my areas of these sections there. So let's calculate the area of this triangle then. Base times height divided by 2. The base is 0 to 10, so the base is 10. The height is 0 to 10, so the height is 10. So it's base times height, 10 times 10 divided by 2. So it's 100 divided by 2. The area of this section is 50. So I'm going to just circle that. Now here's the rest of my shape. Notice that it's still kind of like an oblong weird shape, so I'm going to carve off another piece to make it easier for myself. There's several ways to carve this. There's no correct way or incorrect way, as long as you get a series of different triangles or rectangles, or like I said, if you're comfortable with doing area of a trapezium, feel free. Like for example, you can carve a piece off there and do area of a trapezium on this whole section, but I'm gonna separate it like this. So I have a triangle there and a rectangle there. I'm gonna do my rectangle first. Base times height. So the height I already got was 10. Now the base is from 10 to 16, so my base is 6. Base times height, 10 times 6 is 60. So that's my area of that rectangle there. Now, my triangle. Base is 12, from 12 to 16, so base is 4. Height is from 10 to 14, so height is 4. And it's 4 times 4 divided by 2, and that is 8. So we have 50, add 60, add 8, and that is equal to 118 meters. So that's my final answer. So the distance traveled is basically the area under the graph. So you look at the graph and you take it down from the graph, actual graph line, all the way down to the x-axis. Notice that I ignored all this space by here because that's not area under the graph. My graph stopped just by there. So I took that line down. And it's all that area here that I'm calculating for. If you don't have a perfect triangle or a rectangle, you're going to have to carve your shape up into triangles and rectangles, calculate the areas of each, and then add them all together at the end to find the displacement. Before we finish though, and before I let you guys go off to practice, let's analyze this graph a little bit more, just to get you guys used to and happy with a velocity time graph. Here we go. What if on a question I were to ask you, tell me what's happening in this graph? Sometimes this actually comes up as a 6-mark question where they give you this graph and they just say describe the motion as fully as possible. That's a very common type of question. It might not be 6 marks. Sometimes I have seen it be 6 marks, but sometimes it might be 4 if it's a simpler graph. But usually there would be a question where you're asked to describe the motion fully. Now the best way to do that, I think, when you are being asked to describe the motion fully, is split the graph into different sections of what is happening. So, for example, notice that between 0 to 10 hours, it's a straight line, meaning it's the same thing the whole way through. So, like for example, describing it at 2 seconds, it's not going to be any different to describing it at 8 seconds, because the graph looks the same at each point. So I would split it into different sections based off of what it looks like. So notice that in this particular graph, there's pretty much 3 sections you can split it in. This first one here, the second one there, and the third one here. So, between 0 and 10 hours, what is happening? Well, the velocity is going up over time, and it's going up via a straight line, meaning it's going up at a constant rate. So velocity is increasing at a constant rate. That means then, remember from at the start, when you have this shape, when velocity is going up at a constant rate, that means that it's accelerating or speeding up at a constant rate as well. Object is, or I'll say has, constant acceleration. Now, between the next bit of my graph, 10 to 12 hours, what is happening here? Well, the line has gone flat and horizontal completely. Now, this is where it comes in that you have to remember the difference between a distance time graph and a velocity time graph, because it's different for each. When a line goes flat on a distance time graph, that means then it's stopped. But when a line goes flat at a velocity time graph, it might not mean that. Because at this point, remember, at section number 2, it's staying at 10. It hasn't dropped to 0, it's staying at 10. So it's moving at a constant velocity of 10 meters per second. And then the final bit, between 12 and 18 hours, it's increasing again, so it's accelerating again. Object has constant acceleration. Now, if you really wanted to go all the way and get full marks, you could do a bit of calculations alongside it, such as object has constant acceleration. Well, what is the acceleration? It's gone up. Remember, the acceleration is the gradient of velocity time graph. So it's gone up by 10 over a time of 10. So rise over run, 10 over 10, has an acceleration of 1 meters per second squared. Now, between 12 and 18 hours, it also had a constant acceleration, but it went rise over run. The rise was from 10 to 4. The rise was 4. The run was between 12 and 16. So the run was also 4, meaning it also had a constant acceleration of 1 meters per second squared. Okay. So when it comes to these velocity time graphs, in terms of extracting information, The idea is to be as thorough as possible. Give information directly from the graph. So say between time and time what is happening. If there is a value you can calculate, such as the gradient, do so. And just make sure you're as thorough as possible. And another key bit is just to make sure that in your head you have you've split apart distance time graphs and velocity time graphs, because different shapes mean different things for each depending on which graph you're looking at. So always look at the y-axis first and identify what type of graph it is, and then analyze from there. And then for higher tier students, if you wanted to find the if you wanted to find the distance traveled in a velocity time graph, you would calculate the area underneath. Okay, so now for a bit of practice. I'm going to give you guys the link. Okay, here we go. Right, so on the left-hand side, we have a worksheet for you guys to have a go at, to feel some confidence on. And on the right-hand side is a PowerPoint, just with some quick recap of notes. But the answers to that worksheet are at the bottom of the PowerPoint. So they're at the bottom. So remember, you're not obligated to do all of this sheet. I recommend maybe doing some of it, or basically just as much practice as you can until you feel confident, and then check over your answers. If there's a particular question where you're not sure how I got that answer, let me know via show my homework, email, etc., and I'll be happy to answer you. Okay? Right, guys, so have a good rest of the day. Next lesson, we're going to be finishing off with analyzing motion graphs a bit more and some more calculations before the motion topic will be finished, and then you guys will have an assessment on show my homework. All right? Okay, I'll see you then, and enjoy the rest of the day.